Hello and a very good day. Abdur to Dr. Rahman, our lecturer for rock physics. And today we're going to present to you about our journal review of the sensitivity of elastic properties in determining the fluid type. So to start our presentation, I will explain about our introduction. Rock physics studies has shown the bridge that connected the qualitative geological parameters and the quantitative geophysical measurements. It has become an essential part of quantitative seismic interpretation and a key technology in petroleum geophysics. The elastic properties such as velocity, density, impedance, and BPBS ratio take an important role in reservoir characterization because they are related to the reservoir properties. So in order to analyze these elastic properties, rock physics knowledge will link these elastic properties to the reservoir properties such as water saturation, porosity, and shell volume. And as the result, it will be able to use for lithology and fluid identification and characterization. Accurate determination and understanding of lithology, pore fluid, pore shape, and sizes are the fundamental to the other petrophysical analysis. So in this general review, we will analyze the sensitivity of elastic properties in determining the fluid type by using several types of approach such as Poisson's ratio, P impedance and S impedance, lambda Muro, and lastly SQP/SQS. These elastic domains have different kind of way in analyzing the elastic properties in discriminating the fluid type, as the accurate determination of lithology and pore fluid is an aid for decision making in hydrocarbon exploration. Poisson's ratio is defined as the lateral expansion compared to the longitudinal contraction for longitudinal load, or ratio of strain to longitudinal strain. It characterizes the relationship between Vp and Vs, which the magnitude will be used to differentiate different lithology and fluid. The P wave and S wave alone is very helpful in identifying the fluid, and then the combination of both creating Vp and Vs makes the ratio even more sensitive to change of fluid type than the use of Vp or Vs itself as separately. And past researches has shown that the Poisson's ratio has a very good application effect in fluid identification, especially in gas sand. And there is a precise relationship between Poisson's ratio, pore pressure, and fluid type regarding abnormal formation pressure, neither overpressure or no underpressure. So from the derivation of velocity, this is the formula of Poisson's ratio.
Assalamualaikum and hello. I will be explaining about S impedance and P impedance. So basically here, acoustic impedance or P impedance is the product of density and velocity P with velocity. However, shear impedance or S impedance is also similar, where it is the product of density and S with velocity. Just for an example, if a lithology is known and the P impedance was obtained, the interpreter could predict the rock's porosity. Moreover, the combination of impedance at well and impedance from seismic data, the interpreter could also show and somehow predict any hydrocarbon presence across a certain survey. According to a research by Inchinbia 2014, P impedance versus S impedance cross plot obtained from a certain well is key to understand the behavior of sands with different fluids. However, it was estimated that shear impedance data are less reliable than elastic impedance. It was also determined that both elastic and acoustic impedance data are reliable to be used in specifically distinguishing the gas sands. This is based on with Combi 2002. So if you can see in the slides, that is the formula for P impedance and S impedance. Alright, now so if you can see in the slide, there is this is basically an example from Google Field in Nigeria data. They are using S impedance and P impedance cross plot. So from the cross plot, we could say it's a good discrimination between hydrocarbon bearing sand and the shale. However, the brine sand and shale is difficult to delineate, as overlapping values of brine and sand could be observed in the slide. Alright, now for the lambda Muro method. Okay, in the 1997, Goodway and others has introduced a method of using Lame's parameter in detecting and determining lithofluid boundaries. So up until recent years, it is derived to be the lambda Muro method. This is a method of AVO where it is to extract data volumes of Lame's elastic parameters with the combination of density, which displays in the form of lambda rho and mu rho. For lambda rho, it is the multiplication of the incompressibility by the density, while mu rho is the multiplication of rigidity by density. So basically, lambda rho and mu rho could demonstrate and show significant advantage in the isolation of both lithological sand shale and gas zones. It is an example and a significant method of seismic interpreters to identify hydrocarbons and reservoir rocks, while basically fully utilizing advanced AVO analysis. So below the slides are basically the formula. If you can see the acoustic impedance and shear impedance involved in the formula. So based on this slide, is basically, as you can see, is a cross plot of lambda mu rho or lambda rho versus mu rho based on Niger Delta oil field. So we could see the separation of 4 zones, which are the black circle is probable shale, the yellow circle is brine, and the red circle is basically oil, and lastly is the gas zone, which is confirmed has the lowest density value, which is in the blue zone, blue circle. Okay, many different lithologies could also be identified by the cross plot of lambda rho versus mu rho. This is possible because each lithology has a different rock properties. This response to our subject of fluid content and maybe even mineral properties.
Assalamualaikum warahmatullahi wabarakatuh. Okay, for my part, I will talk about SQP, SQS. The newly attribute, namely SQP and SQS, which are derived from attenuation by using rock physics approximation, give some significant improvement in determining the lithology and pore fluid effect for hydrocarbon distribution prediction. In the future, the SQP, SQS attributes can be used to replace the gamma ray log and resistivity log, and respectively for the same purpose. For example, phases classification, formation evaluation, reservoir characterization, and petrophysical properties prediction. The SQP and SQS are formulated as on the slide, where M over G is the ratio of bulk and shear modulus that can be approximated from the P wave and S wave velocity ratio equation. The equation shows that all the parameters in this equation can be calculated directly from the seismic inversion result, with density and VP over VS as inputs. In the SQP-SQS cross plot, the effect of lithology are distributed along the vertical axis, which is SQP, while the effect of water saturation is distributed along the horizontal axis, which is SQS. The beauty of new technique is that both of the effects are separated orthogonally. In the SQP-SQS cross plot, shale and sand lithological effect, which is are distributed in the SQP, and various water saturation, which is fluid effect, are distributed in the SQS. Both effects are separated orthogonally to each other based on the figure. In these nutrient attributes, the hydrocarbon reservoir can be located in the low SQP and high SQP. Based on the figure above, which is SQP and SQS log response of SQP and SQS attributes are similar with gamma ray and resistivity response respectively. Therefore, the SQP can be used as a lithology identifier tool and SQP as a fluid identifier tool. Coal is identified as high SQP and SQS, while gas is low in SQP and high in SQS. Hence, it's easy to distinguish gas from coal. This is beneficial to the interpreters to solve the ambiguity issue between the gas and coal layer. For the methodology, this journal review analyzed a different application of elastic domains such as Poisson ratio, P impedance and S impedance, lambda Boro and SQP and SQS. These parameters are estimated from well data using each equation where the inputs are derived from well log. To correlate these parameters with hydrocarbon content, we studied the results from different journals where the field has been examined. Cross-plot, trend analysis and the contrast has been analyzed to show the performance of the parameters in determining the hydrocarbon. Finally, the performance of these parameters were compared to each other to identify which one is the best fluid indicator.
So now we are here in the discussion part where we analyze each of these elastic domain based on its advantage and disadvantage. So the first one, Poisson's ratio. This method has a very good effect in tight reservoir layers due to its high sensitivity in low to medium type of porosity and permeability. However, it is not very effective in a shallow sand reservoir, as the shell content cause the reading of PR scattered with high values. For P impedance and S impedance, this method is used to identify pore fluid. Okay, so based on the case studies that we analyzed from research papers, this method is very reliable on gas sense type of lithography. But however, it is not very efficient in separating the fluid and the lithology, because this method is more to analysis of the anomalies of rock physical properties, and actually doesn't show any significant changes in other type of lithofluid other than gas sense. And when dealing with more type of complex geological condition, this method is really not recommended. Hence, to improve the pore fluid detection and lithology discrimination, we apply the lambda Muro method. So here we have two diagrams. The left diagram shows that the effectiveness of the Poisson's ratio as it detects all the hydrocarbon layers that they observe in that particular area. However, for the right diagram, this graph shows that due to the presence of shell content, it caused the Poisson's ratio reading to be less sensitive as it affected by the shell content.
Right, after a thorough discussion here, based on lambda Muro, we could conclude that it has an advantage to determine geological trends and elastic parameters. It serves the purpose of assessing reservoir quality and economic viability. It is most effective in wells that bears gas sands. However, it is not advisable to be used for wells that bears oil sand and water sands. This is because the sesame readings basically to be overlapped. Okay, so due to this, the interpreter will have some difficulty to distinguish the lithofluid boundaries. So for SQP and SQS, it has the advantage of classifying phases, reservoir characterization, petrophysical properties, prediction, very high contrast of gas sand, and it is invulnerable with the lithology. So in comparison of other fluid indicator, SQS and SQP has the highest correlation values with water saturation curve and very high contrast in lithofluid detection and differentiation. We analyzed that the effect of lithology on Poisson ratio and lambda mu rho is still high, but not on SQP and SQS. Hence, it can be concluded that SQP and SQS is the best fluid type indicator.
Okay, for the conclusion, there are various methods to determine fluid type, and the effectiveness of each method are dependent on the rock properties itself, as it will be different for various fields. For a sand-dominated well, it will be convenient to use the conventional rock physics method such as Poisson ratio to separate the lithology and fluid type. However, if the well is dominated by silty sand or shale, silty sand or shale, it's difficult to distinguish the pale sand based on the previous method. Hence, the most suitable method is the SQP and SQS, as it managed to display a clear separation of hydrocarbon sand from the background trend and different lithology. The SQP and SQS is sensitive with pore fluid rather than lithology change, but anyhow, our interpretation and prediction will be much accurate and clearer if we are applying all these parameters, where we can compare and contrast the results.